In this video, we're going to take a look at section 9.1 in your book and try to summarize some of the important ideas. Since this section is more conceptual than it is procedural, what we're going to try to get at are what are the big ideas you need to take with you. It would be good for you to have your book. I will be referring to some specific things that should be in your notes as we go through it, so you might want to have your notes handy as well and pause the video whenever you need it. We're going to start on page 562. And on that page, we did do activity 9A, and we did in class. And so if you were absent on that particular day, or if you just don't quite remember the activity, I'm going to summarize a couple of the main findings that we came up with in this particular case. We were working with the heights of young women, and you might remember that we looked at two distributions. The actual distributions of the heights of those women, which I'm going to sketch here on the screen, and that particular distribution was approximately normal, and we knew its mean and standard deviation. Its mean was 64.5 inches, and if we went 3 standard deviations above or below, we knew we were going to be between 57 inches and 72 inches for 99.7% of all young women. And so what we then did is we said, well, what would happen if we took samples of size 100? Now, we would like to, if we somehow could, to take all possible samples of size 100, but that's just, there's no way we could possibly do that. So we took a sizable number of samples, around 60 per class, and we calculated the average from each one of those samples. And if you recall, that made its own distribution. It was also symmetric. It also had its height at 64.5, but it was smaller in terms of its width. So, for example, it might have looked like this. Same peak, but definitely skinnier. So the whole distribution might have fit in about that much of the original distribution. So it had the same value for the average, same mu, but it had a smaller value for sigma. And that wasn't unique for the particular type of data that we were working with or the particular size sample that we saw, although we did say as n increases, we would expect that the variability of the sampling distribution was going to get smaller and smaller. And in fact, that's what we built, something called a sampling distribution. So one of the important ideas that you want to make sure that you have in your notes is that a sampling distribution is literally a distribution of a key statistic from every possible sample of a given size. Okay, so you definitely want to have that definition in your notes, and I'm going to give you a page number here. The page number for that particular idea is on page 567. And it just says the sampling distribution of a statistic is the distribution of values taken by the statistic in all possible samples of the same size from the same population. It is important that you note they're from the same size samples. So I wouldn't be comparing samples of size 10 to samples of size 100. The other thing that we saw, and this was a picture that I put on the board, so if you didn't put this in your notes or you were absent, you might add it. We said, let's imagine that we have our population here. And we also have a sample from the population, which looks a whole lot like it. It's just smaller. And in this particular case, we want to compare certain things about the two. We talked about the fact that when we talk about the population, we're always going to use the term parameters. Parameters are numbers. And whenever I say, is this a parameter or what parameter are you using, that always means I'm talking about the population, not a sample. When I'm talking about a sample, I'm going to use the term statistic. So it's really important that you separate those two in your head. It's also important to note that in a population, if I would talk about mu being the average, in the sample, I would talk about X bar as corresponding to that. If in the population, I'm talking about sigma, the standard deviation, in the sample, I'm going to use the letter S. And if in the population I use the parameter P, which here does not stand for probability, although it's kind of related if you think about it, it stands for a proportion like a percent of the population that has a particular characteristic. In the sample, I'm going to use p hat. So it's very important that you can not only identify those terms, but that you put the correct labels on them. All of our formulas are going to consist of these letters, and so if you're not sure which letter to use, you're in big trouble. Okay, the last thing that we did with this section is we read a chunk of it from pages 573 to 576. And we constructed 25-word summaries of what we read. Some people did about a 25-word summary or so after each subsection. The first subsection is called the bias of a statistic. The second one is called the variability of a statistic. And then the third one kind of ties them together and talks about both bias and variability at the same time. I would tell you that's a great exercise to do. If you want to pause the video, it would be ideal for you to do that exercise. And then I'll kind of summarize some of the important things that you would need to have in your summary. So assuming that you've done the exercise of your 25-word summary, what are some things that you wrote? Well, one of the things a connection that you definitely want to make is the fact that bias as a concept is really focused on where the center of a sampling distribution is. If bias is present, it means the center is sort of off target, and in general it will be shoved off target in the same direction. So I think the photograph or the pictures on the very last page are really useful for that. If you have variability, on the other hand, what you're really talking about, what you want to connect it to, is spread. So ideally what we really want for a statistic is we want both measures to be low. And that's shown in the picture on the very last page. In fact, I recommended in class that you actually take those pictures and sketch them into your notes so you have an idea of what they look like. Remember that low bias would mean that I'm close to the actual target. Low variability would mean that I'm not very spread out, and so my measurements are very consistent. High bias would mean even if I have high bias, let's say I have low variability but high bias, I might have very consistent results, but they're very consistently off. If I have high variability and high bias, it would mean that not only am I not centered on the target, but also my data are very variable. That's the worst possible scenario. The last thing that I want to make sure that you have in your notes from this section is this notion of an unbiased estimator. And that's actually summarized near the very beginning of this section. And I will find the page number for you. It's in what you read. It's on page 574. In an unbiased estimator, it says, a statistic used to estimate a parameter. Remember, we would use a statistic to estimate a parameter because usually it's from the population, and so we don't know what it is. But a statistic is unbiased if the mean of its sampling distribution is equal to the true value of the parameter. And the statistic is called an unbiased estimator. Obviously, that's really what we want as often as possible. And if we can find one of those estimators and we can try to reduce variability, our estimates are going to be extremely reliable. This kind of summarizes the main ideas from section 9.1, so please make sure that your notes are updated.